Okay, so let's start the 22nd lecture. So the topic of this lecture is to compute. I think I have. To compute the dimension of the space of Hodge cycles. Hodge cycles, of course, for our main example, for Fermat variety. And maybe before going to this computation, I tell why we are doing this one. Because a typical way to prove the Hodge conjecture for smooth projective variety is this way. X is smooth projective. So just imagine that you have a projective variety and you want to prove the Hodge conjecture for X. So one typical way, let's dimension n and even. So I will denote the space of Hodge cycles by this. And at the end, the Hodge conjecture is our rational numbers. Even so, it is nice to consider our integers and to study the failure of Hodge conjecture of our integers. But and I will use this notation. Then the classical notation is this one, which is intersected with h and x q. Anyway, why we want to compute this one? The reason is this. Okay, so the main interest is to verify the Hodge conjecture for X. So just imagine that I have cycles. So I compute this number. Let's call it A. Okay, and then I find algebraic cycles Z1, Z8. These are algebraic cycle in X, so dimension of Zi is n over 2, and for this reason they induce elements in the homology, and at the end of the day this guy is for me is inside homology. That's why I have changed the notation from this classical notation to this one, because almost no book consider in homology. But anyway, and so this will give me elements in the homology, and we have seen that these are Hodge cycles. So this will be Hodge and xq. And for just this one we will discuss, just assume that ZR are linearly independent in H and xq, and this is inside. So if we construct A algebraic cycles which are linearly independent in their homology class, in linearly independent in homology, then this is we have already verified the Hodge conjecture, because we know that Q Z1, Q Z2, blah blah blah, this subspace generated by CI is inside Hodge and XQ. This is of dimension A, and we have also A linearly independent elements there. This will imply that at the end of the day, this is this is the equality. So the Hodge conjecture is verified. Any Hodge cycle is a algebraic cycle. That's why computing the dimension of the space of a Hodge cycle is important, because in this way we know how many algebraic cycles we have to construct. At the end of the day, this computation is still it's difficult, but I have to say that the most difficult part of the Hodge conjecture is not the computing the dimension. It is the constructing these algebraic cycles. So in the last lecture, I will explain a little bit how to handle algebraic cycles and so on. So to construct a algebraic cycle such that they are linearly independent in homology, and they is the difficult part of the Hodge conjecture. And in general, we don't have any procedure in algebraic geometry which construct for us algebraic cycles, just enough algebraic cycles of a variety. It's a kind of handling a Diophantine equation. Okay, so this is the justification for why one has to compute the dimension of Hodge cycles. So let's go back to the hypersurface case. Again, what I am saying, it is valid in general for hypersurface. So let's remember that let's say X Fermat variety of degree D dimension n, Y the same variety of the Fermat variety of dimension degree D dimension n minus 1. It was given by x0 equal to 0 intersected with x. And okay, so let me say a few words. So in general, the most famous algebraic cycle that we have in a variety, let's say in a hypersurface, it is the intersection of some linear p n half plus 1 intersected with x. So it doesn't matter which projective space we take, because at the end we will take the homological class of Z infinity. For example, I will take Z infinity will be this x0, x1 until x and half. Let me see, minus 1 equal to 0. And in the way that I have chosen this Z infinity, of course, this Z infinity, it is inside my Y. Okay, so something was not clear in the last lecture. Let me remember that I called L the affine part. And the idea was that to capture Hodge cycles using the affine part of the variety. Okay, so remember that then H, N, L. I will mix homology and cohomology with integers and with the rational numbers, but at the end, for concrete computation, I will do our rational numbers. So let's write this Gaussian sequence Hn minus 2 yq. Then there is a 0. This is the Gaussian sequence that we have already used many times. We know that this is H by Hard-Lefschetz theorem. We know that this is Hn yq, and at the end these are hypersurfaces by Lefschetz hyperplane theorem. We know that this is one dimensional, and actually in this case, if we call it the infinity, maybe let's do our rational numbers, and the integers you can read in the book. So at the end, this is generated by Z infinity. Anyway, this tau map was the intersection of cycles, and so so here remember that we had our delta betas. So the one observation that I want to make is that Okay, so h n x q primitive part, which is usually also called prim, but I will put 0. In my book, there is over 0, there is some check. This has to do with the torsion stuff, but let's forget the torsions. In particular, working over rational numbers, we don't need to talk about torsions. So this is the kernel of tau. So, and okay, so it turns out that, let's say, HNX Q, this is just it's primitive part plus this z infinity part, and the reason is that if you go z infinity here, the z infinity maps to let me say in this way. If you intersected this, let me. So this doesn't. This goes to something non-zero. Non-zero, and which eventually actually will be what? So if we make a Pn, let me say in this way, Pn minus 1 intersected with y. Let me see if it is, yeah. Which again, it is the generator of this guy. Anyway, at the end of the day, if we want interested to understand Hodge cycles here, we just need to understand the Hodge cycles here in the primitive part. And then maybe I have to say something also, which is important. This is
Hossein,
Fal.
can you recall why Hn minus 2 of y is isomorphic to Hn of y?
Which one? With the
This equality, yeah.
this one. This is the hard dimension of y is n minus 1. N minus 1. And remember that there was this hard Lefschetz theorem. So it was one dimension below. Let me write in the cohomology. Hn minus 2 y going to Hn y. So n minus, write n minus 1, n minus 2, n. And by hard Lefschetz theorem, the cohomology is below the dimension, and above the dimension, in a symmetric way, they are isomorphic. And this what was this map? This map alpha going to alpha cup with the polarization. So the map was alpha going to alpha. Let's say cup. Actually, the Poincare dual of this infinity. No. Sorry. This is the class of the hyperplan section. I called it theta. Anyway, this actually I will not use this one. But anyway, this isomorphism comes from the hard Lefschetz theorem. And by hard Lefschetz theorem, the cohomology is below and above the middle cohomology. They are isomorphic by some cup product.
Okay, thanks.
But anyway, the most important thing is that what I need, that this tau delta is 0 if and only if the intersection of delta with this z infinity, this one, I will need. So the primitive elements are exactly those elements, and this pairing is pairing in HNX Q HNX Q to Q. And actually, this isomorphism I have used here because because remember that tau delta topologically was delta intersected with y, and this gives me a homology class in H in Hn minus 2 y q, and yeah. Anyway, so just something that I wanted to you carry in mind, that the kernel of tau corresponds to those cycles which are perpendicular to these elements in the homology. And yeah, so maybe it's something I have to. So again, I remember the Hodge cycle. So, and anyway, kernel of delta are the images of this one. This means that at the end of the day, Hn, remember that delta beta here form a basis. H and X primitive is spanned by delta beta. And anyway, this means that at the end, since this guy is already algebraic, so in order to understand Hodge cycles, I have to just focus on this part. So maybe I write the definition of Hodge cycle that we get last time. Hodge cycles. So we have to, well, it is span, so we have to take some combination of delta beta. So C beta are rational numbers, beta in I, and this integrals must be 0 for what? For all beta, it must be not integer, and beta must be less than n half. Yeah, and beta is in our index set I. Okay. So at the end, we have this inconcrete definition of Hodge cycle, and remember that we have already computed these integrals. Anyway, before going to compute concretely the space of Hodge cycles, let me say about the fact that we have a lot of trivial Hodge cycles because these deltas are in the affine part. So at the end of the day, I will work in, I will consider this one in HNLQ. And for this reason, I have to take care about cycles here, which are mapped to 0 under the inclusion. So maybe, okay, cycles at infinity. So, well, I have to a kind of width way to get away from this. So let's write the inclusion. So anyway, if you take a delta here, some n, what I called C beta, delta beta, beta in I. There are some of them which goes to 0, and of course I want to get rid of these cycles using just topological method. For it is possible to see which cycles goes to 0, but in order to understand these cycles at infinity, and I call these cycles at infinity, the reason is this one, because we have X, and at the end of the day, these are cycles which are supported around this Y. Because when we put back Y inside X, they must homolog to 0. So this means that they shrink to points. that's and at the end the y for me is at the infinity, and these cycles also I call them cycles at infinity. Anyway, in order to have to be able to handle these cycles also, because in our way of definition of Hodge cycles, this will be automatically also Hodge cycles, because all the integration that we use in the definition of Hodge cycles is also zero over this one. So for this one, I have to say about maybe not too much H and the Rham. The same decomposition that I made in let's say C vector space generated by omega beta in I, this and a beta not integer. So in a way we have this plus C, the Poincare dual of this infinity. Anyway, in the Rham cohomology side also, we have this decomposition. So first we have this. This is actually this H and the Rham X primitive again. I could define it in a more intrinsic way, but anyway, let's call this NHM primitive, and it turns out that this decomposition is dual to this decomposition Q vector space generated by delta beta, but these are might be in plus Q Z infinity. Anyway, if you tensor this C instead of Q, you using C, then you will have this decomposition. Anyway, there is this one dimension that always we have to care about. Our integral, so we can do it, but it will be a little bit more work to write down the things explicitly. This has to do with the polarization, polarity. And it turns out that this guy is by the Rham theorem. This is dual to this part. And let me. Okay. So what I need to what I will need is this one, delta. So if I start working the affine is what? So cycle infinity is the one, as I said, the cycle here which goes to zero after compactifying is a cycle. It's a cycle at infinity. If for all beta in I are beta not integer. Anyway, I am taking, so if the integration of all these guys over the cycle is zero, this will be the cycle at infinity, because as I mentioned, this is the dual of this guy here. So if the integration of all these elements here over some cycle here is identical to zero, so this guy will be zero itself. Anyway, maybe I could try to write explain more, but let's keep this one. So delta, when I am working in the affine variety, delta is Hodge if all these integrals are zero. And remember that the Hodge cycle was with this one with additional constraint that a beta is less than n half. So the moral of the story is that H and a space of Hodge cycle for Fermat variety, the primitive part, will be, let's write down this one. It will be delta C beta delta, combination of these guys, such that omega beta delta is equal to 0. So beta in I, beta not integer, and then beta less than n half. And of course, there are a lot of trivial cycles here, the one coming out from the infinity. So this will be delta, the same, beta in I. So this is the isomorphism. In I, beta not integer. So this is a subset of this one. So at the end of the day, the space of Hodge cycles will be for me this one modulo those that are zero in homology. In order to capture the zero in homology, I use these cycles at infinity. Anyway, so now we are ready to compute the space of Hodge cycles. Any question? Okay. So in order to be able to implement the things in computer, so let's write the period matrix. So I will write delta betas in the rows, and this omega betas, omega beta, such that let's just take the one that we need and not integer here. So and let's see which one will be beta prime. So at the end I will integrate omega beta prime. So it's beta prime entry is this integration. Okay. And okay, let me write something else also. Remember that our formula of the integration. Our formula of the integration, there was a transcendental part, and maybe I remember this one. Okay, maybe just inside the text. If let me write this one. Okay, there was a two part. There was a first part depending only on beta prime. Let's this it was something like -1 to the n m. Let's say in our context, I equal, maybe I write it to the Fermat in the case, d to the n plus 1, and then there was beta 1 plus 1 d. I'm making the substitution beta n plus 1 prime d, and so on. But this guy depends on just the differential form. But let me. Oops, sorry, what happened here? So the point is that this integral equal to 0. So this transcendental factor can get out. So that at the end of the day, this Hodge cycle doesn't depend on the transcendent, this gamma factor of my differential form. It will just I will just need the beta factor. So the moral of the story is that for the definition of my Hodge cycle, I will just need let's call this transcendental factor b beta prime. For the moment, I can forget this one, and this I in my period matrix I will just use the the algebraic part. Now, so let me write here the algebraic part in our context, zeta d to the beta I plus 1, beta I plus 1 minus, so it is getting out of matrix, zeta d beta I plus beta I prime plus 1. Anyway, so what is for the definition of the Hodge cycles, what we need? So this will be the period matrix, and remember that at the end we need something. What is a Hodge cycle? I have to put my C betas in a let's say one times mu matrix. So at the end of the day, this is mu times some mu check matrix. I know what is mu. Mu is d minus 1 to the n plus 1. It is the number of delta betas. Anyway, C beta are integers. So what is so the integral that we have written here? This 1 times mu matrix times certain columns of this matrix equal to 0. And okay, so let me okay, so let's call this one P matrix P. So let me n half. What is the notation in my? Okay, n half plus 1. So let's define this one also the same. Here delta beta, but here in the columns, let's put the one that we need for. So we will put omega beta and a beta less than n half. Okay, so the moral, and again, let's just put the algebraic part of the integration. So Hodge cycles n xq will correspond to what? Let's write down now explicitly. So it will be the C matrix. Let's call this C matrix. C in matrices. How many? 1 times mu matrices with coefficients in Q, such that C times P n half plus 1 is 0. This is in the kernel of this matrix. Modulo C, the same C, such that C, this P, equal to 0. And this is now the translation of our Hodge cycles to a more computational context. Okay, any questions so far? Okay, so what we have a matrix. So the point is that we have a matrix. So mu times mu check, and let's say where it is defined in these roots of unity. And there are many computer programs that you can implement this one, but maybe in order to compute the Hodge cycles, let me say a few words about this. So these matrices are defined over Q zeta D, but the vector C itself, it is defined over Q. So we are interested in a rational value, the vectors which are perpendicular to a matrix with zeta D coefficients. And at the end, this is not just this is an equation. In the number of equations here is the number of columns of this guy. But if we write if you want to write it as equality only in rational numbers, it will get more. Maybe I explain this one. Okay, so in order to make the computation, let okay, let me so I have to the Tn cyclotomic polynomial phi dx. So what is the definition of cyclotomic polynomial? It is the minimum the polynomial of minimum degree which annihilates phi. So it is x degree is minimum such that phi d zeta d is equal to 0. And okay, let me, and what else I need? So first of all, it is known that this has an actually integer coefficient, but let's it's a polynomial in x. So in order to compute what it is degree, let's degree of phi d, call it this phi d, which is I think they call it Euler number, I don't remember. Anyway, it turns out that 1 zeta d 2 zeta d phi d minus 1 form a basis of this extension q with zeta d and then q. And so so we have by definition we have this basis of q zeta d over q. So let's come back to our definition of Hodge cycles. So let's take a p or this p and half plus 1. So at the end of the day, I can write this one as p0 plus p1 zeta d blah, 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 p phi d minus 1 zeta d phi d minus 1. And now these pi's are matrices of the same mu times mu check with rational coefficients. And what I want to do at the end, I needed this equality, but this equality then will be break into CP0 equal to 0, CP1 equal to 0, and then CP PD minus 1 equal to 0. Anyway, what I wanted to say that this in the definition of the for computing Hodge cycle we need this equality, but in order to do computation in our rational numbers, I have to break it. I have to get matrices with integer coefficients, and then this equality will be broken into phi d equalities, and at the end of the day, let's return back to our our
Hossein,
part.
for me, it's not clear why you need to use these cyclotomic polynomials and to get this
Okay.
this decomposition.
So, no, first of all, I need the degree of the cyclotonic polynomial. It is this Euler function. Let me actually write this phi d.
Yeah, no, this is clear.
Uh-huh.
But I don't see why do you need them?
I need here, I have an equality involving complex numbers, and I want to say that this equality is the same. Is this decomposition is clear? Because at the end, this is because of this. 1 zeta d zeta d to the t, they generate this.
Yes, this is okay.
So this will imply this one. And at the end, I want to say that Cp equal to 0, C with rational coefficients, if and only if this one. Because if this is equal to 0, then we will have Cp0, Cp1, and so on. And there is no linear relation between these guys. So this is the point. There is no linear relation between 1 zeta d to the d and zeta d to the phi d minus 1 over rational numbers. So this means that if this is Cp0 plus Cp1 zeta d blah 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 Cp phi d minus 1 zeta d phi d minus 1 equal to 0. Yeah. So this, since there is no relation and now these are all rational matrices with rational coefficients. So each entry will give me a linear relation between 1 zeta d and zeta d to the phi d minus 1. And since there is no linear relation with the rational coefficient, it will imply that Cp0 equals to 0, Cp1 equals to 0, and Cp phi d minus 1. So what I need a basis. What actually I need is the basis of this guy. I will not need the cyclotonic polynomial itself, but I need this basis. And maybe I would say where the cyclotomic polynomial pops might be used, because anyway, you see that it is a mixture of zeta d's, but at the end I have to write it everything, and I have to write everything with the power of zeta d strictly less than phi d. And if let's say phi d zeta d is zeta d to the phi d plus blah 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 blah. Yeah. What this means, whenever I see a power of zeta d bigger than phi d, I just replace this guy with this rest terms here, and each time I reduce the power of zeta d until reaching in a point such that I have only the power 0, power 1, and the power phi d minus 1.
Okay, I see.
Anyway, for the computation, it will be needed, and let me say the most important thing that for our discussion is that 1 zeta d and zeta d to the phi d minus 1 are linearly independent over Q, and they generate this vector space for me. Okay, so let's go. Okay, maybe I will not show the computer elemental implementation of this one, because anyway my computer abilities also is very poor. But at the end, let me just show some table. So today I was talking about this section 15.5, blah, blah, blah. I skipped a lot of things. As I said, for the discussion of the Hodge cycles, we really we don't need this beta factor. In the next lecture, we will see that this beta, apparently transcendental factor, they are used. And actually, in this way, Hodge theory has one direction going in more in transcendental number theory. Okay, so the idea is that at the end, everything becomes just a heavy linear algebraic form. These things at some point I will talk about. This the intersection of delta betas, because we will consider the space of Hodge cycles as a lattice where there is some integration. Anyway, all these, so if you see check notation, you can ignore it, in particular for hypersurfaces, and in general if you are working on rational numbers. So it is, don't worry about this one. This is the same thing that today I called. And again, this preparing the ground to do for computation, so writing the period metrics and so on. And as I said, I have one has to break. So this is the thing that now I explained now. So I have to break my metrics into rational valued metrics in order to be able to do computation. And so this is just a kind of to be able to compute with the computer, because a priori there is no closed formula for the dimension of the space of Hodge cycles. So this means that at the end, what I'm saying, I don't know any closed formula for this number. And something this is a kind of maybe I didn't mention at the end, really what one needs to compute the rank of this matrix. But anyway, maybe in one moment I will tell you. But since everything is concrete, then you see that one can compute. Oops. So the space of Hodge cycles. So for the by the classical presentation of the space of Hodge cycles, it is clear that the dimension of the Hodge cycles must be less than the Hodge number hn half and half. So in this case, if this table is for n equal to 4, and then the degrees vary. Here is the degree. So maybe let's just forget this the trivial cases. So in degree 3, we have a kind of the space of Hodge cycle in 21. In degree 4 also, and this is the maximal one, because as I said, H22 is the maximum for the dimension of the space of Hodge cycles. And you see that in in degree 5 it is 401, and this is just the implementation of whatever I explained right now. And then you see that here the sign question, because by my computer I was not able to compute these numbers. And maybe let me say something else. Okay, maybe I tell anyway, let me see what I have some time. What can I talk about? Maybe just one observation. Where is this observation? Okay. Okay, I will talk about a little bit about this this observation. And okay, so in the way that I presented I presented the Hodge cycles, at the end the Hodge cycles are defined modulo cycles at infinity, because cycles at infinity will pop up in our way because we wanted to study Hodge cycles supporting affine variety. And at the end, a Hodge cycle is defined modulo these objects. So it is a kind of desirable to try to fix a representative of Hodge cycles. Maybe so. So so there is no canonical way to choose mu elements of delta beta such that they form a basis of this Hodge cycle. So whatever you see z, just put the rational numbers. That's and it turns out this is a kind of a very uh, strange observation. So it turns out that uh, if we allow integers, so this you see that here a beta, if we define delta cycles such that integral omega beta over delta is equal to 0 for all beta with a beta integers also. So as I said, this a beta has to do with this omega beta has to do with the Rham cohomology of the infinity. This is why. Anyway, this becomes isomorphic exactly to the primitive part of the homology. This means that if in order to get rid of cycles at infinity and to take a unique representative of the Hodge cycles, we may ask also that the integration over integration of omega beta with a beta integer also to be 0. Okay, so let's go back to the camera, and then I will say continue the discussion here. No. Okay. What I wanted to say is that at the end of Hodge cycles, delta are defined as cycles at infinity. And the observation that I have made there is that if you just there is a beta not in integer. If you just remove this one, if you remove this one, this will be 0 by the Rham theorem. And at the end of the day, the space of primitive Hodge cycle will be delta such that omega beta delta equal to 0 for all beta in I, such that a beta is less than and half without this restriction. And in this way, you will get what you will get. You will get a unique representation of Hodge cycles in terms of, well, at some point I have to explain main, but these delta betas are spheres and cold vanishing cycles in terms of vanishing cycles. Anyway, I think so far so good. So the moral of the story that we in practice we can compute the dimension of the of Hodge cycles. Okay, maybe I stop recording and then I will say something.